A particle is in the ground state of the harmonic oscillator with classical frequency omega, when suddenly the spring constant quadruples, so omega prime is now 2 omega, without initially changing the wave function. What is the probability that a measurement of the energy would still return the value h bar omega over 2? So first, let's write out our basis, right? So initially, before the spring constant quadruples, right, our basis was psi 0, and let's just call this psi 0 I, right, because this is the basis before we quadruple it. So this was m omega over pi k to the 1/4 e to the negative m omega over 2 h bar x squared. After we quadruple our spring constant, right, that means that our omega is now going to be 2 omega, meaning that our basis after we quadruple the spring constant, we'll just call this f, right, is now equal to m times 2 omega over pi k e to the negative m 2 omega over 2 h bar x squared. Now, what are the energies for the before and after? So before we quadrupled the spring constant, right, the allowed energies for this basis here, right, was h bar omega times n plus 1/2, where n is an integer. Right? So how would we get h bar omega? So when would the energy here, right, be h bar omega over 2? Well, that's easy. That would be in our ground state when n is equal to 0, right? Because when n is equal to 0, our ground state energy is h bar omega over 2. But now, after we quadruple the spring constant, right, our energies become h bar times 2 omega n plus 1/2, where n, again, is still an integer. So now we want to find, right? So now we want to find for which state is our energy, right, going to be equal to h bar omega over 2. So let's see, we can cross out the h bar omegas, and so let's see, so then we'll have n plus 1/2 is equal to 1/2. So then we have 2n is equal to negative 1/2, and then n is equal to negative 1/4. Now, this isn't good because n has to be an integer, right? And n cannot be a non-integer, meaning that this is not allowed. So our final basis cannot have an energy of h bar omega over 2. But how about h bar omega? Can it have an energy of just h bar omega? Well, sure. So h bar omega, right? So when is the energy here going to be h bar omega? Well, this would be in our ground state, right? So after we quadruple the spring constant, right, our ground state energy is just going to be h bar omega. So how can we find when the how do we find the probability that our wave function will be in the ground state and have energy of h bar omega? How do you find the probability, right, that we'll have h bar omega? Well, the way to measure that is to first write our original wave function, right, the actual wave function, in terms of our new basis here, right? And then we'll find that the coefficients on these, the squares of the coefficients in front of each energy level, right, will tell us the probability of getting that energy. So what we need to do is that we need to find the coefficients. So to do that, we know that well, first of all, to find the coefficients, so we can just take an inner product of our new wave function we can take an inner product of our new wave function, which is the complex conjugates of psi 0 star, with our original wave function, which was just psi 0 I. And we're trying to find the probability when n is 0, right? Because that will tell us for this energy. So C0, oh, excuse me, this should be psi n, it's here. And then for the ground state, then it'll be this inner product here, which will be 2m omega over pi k to the 1/4 times m omega. Oh, excuse me. You know what? I just noticed that these should have all been h bars. And then this will be the integral from negative infinity to infinity of e to the negative 3m omega over 2h bar x squared dx. Now, to evaluate this integral, we can use the formula that in general, an integral from 0 to infinity of the form x to the 2n e to the negative x squared over a squared dx is equal to the square root of pi times 2n factorial over n factorial a over 2 to the 2n plus 1. Now, for our integral here, our n, right, since we're not actually multiplying by an x anywhere, right, our n is going to be 0, and our a will be the square root, so our n is 0, and our a is going to be the square root of 2h bar over 3m omega. So now this integral here will be equal to, let's see, 2 to the 1/4 times m omega over pi h bar to the 1/2 times the integral from negative infinity. And this, important, this integral, right? So this is an exponential function, right? However, our variable here, right, is x squared, which is even, meaning that this integral is even, meaning that it can be written as twice the integral from 0 to infinity, right? However, since it's twice the integral from 0 to infinity, we can use this here with our a's and n's, meaning that this will be square root of pi pi 0 factorial, which is 1, over 1, so that's just 1, times a over 2, so a is square root of 2h bar over 3m omega over 2, all to the 1. So plugging everything in, we get this. And there's a couple stuff we can cancel out with this, right? So we can get these pi's to cancel out. Here, we can get these h bars to cancel. And when we do all of this, what we're left with is C0 is equal to 2 to the 1/4 square root of 2/3, which is equal to 0.97. And then the probability of getting this is going to be CO squared, which is equal to 0.943. And this is the probability of measuring an energy with a value h bar omega.